All right, please go ahead.
Yeah, okay. Okay, so thanks for the introduction and also thanks for the kind invitation from Professor Nima. Today I will introduce the floating point computing memory processor that was published in ISSCC 2023. Some new materials have been added at the end of this talk so as to make it up to date. The outline is as follows, and we will start from introduce the motivation and challenges for a floating point CIM processor. We start from the well-known motivation that wide scenarios AI applications require lower power and high performance. As shown in the right figure, the memory access dominates the power consumption of the digital neural network system. Data access from the DRAM and on-chip SRAM requires several orders higher energy consumption. That's why we need computing in memory architecture. Here we make a simple clarification that most existing CIM solutions, especially the SRAM CIM and also including this work, targets the on-chip part in the red box, while the CIM solutions that try to solve off-chip DRAM access might require much more future efforts. So why we adopt CIM instead of the conventional digital architecture? Theoretically, the CIM solution has two main advantages. Firstly, it doesn't need to obviously read out the data out of the memory array, so the data access energy can be saved. Secondly, it provides high computation bandwidth so that we can have more opportunities to optimize the computation power and area. To support floating point CIM is also very important for many scenarios. One example is that larger models and more difficult tasks, such as the transformer large models, requires higher accuracy. Another example is that the training process of the neural network, including the bypropagation and the gradient update, still relies on floating point operations to retain high accuracy. However, before this work, previous research on the floating point CIM is very limited. Actually, previous work have explored various CIM designs for the fixed point computation, also called the integral computation. The integral computation naturally suits the CIM circuit's design. For the binary CIM, each cell stores 1 bit data, and the computation on each column are the same. For multi-bit CIM, different columns store different bit positions of the multi-bit integral data. Either in the analog or the digital CIM implementation, the operations on each column are similar, so that integral computation and CIM can suit well. But the floating point CIM is challenging due to its special data formats. The standard IP formats including 3 parts, the 10-bit exponent part and the mantissa part. The value of a floating point data can be calculated by the bottom formula. When performing floating point computation, multiple steps are required. For the floating point multiplication, it first calculates the mantissa multiplication and the exponent addition. Then it performs the mantissa normalization and also the exponent shift to get the final result. The floating point addition is also very complex. Such complex operations are difficult to be in-memory implemented. There are mainly 3 types of floating point CIM solutions before this work. The first one is similar to the near-memory computing. It implements floating point circuits or Boolean logic beside each sub-memory bank. The second one divides the floating point computation into the exponent part and the mantissa part. The exponent part runs in CIM domain, while the mantissa part runs in the digital circuits domain. These 2 methods suffer limited row-wise parallelism. The third solution is more widely used, is to expand and align the floating point number into the fixed point form so that it can be implemented in the same way as the fixed point CIM. However, it may require very long integral bits, which may lead to many CIM execution cycles. This work starts from the third solution and show why it's still challenging. The first challenge, as just mentioned, is that directly IP alignment may lead to many execution cycles. To align different IP data, the same bit and mantis part need to be shifted left or right according to the exponent value. As shown in the top figure, the exponent value of the floating point data shows the Y distribution. In the extreme case, the alignment of the IP16 requires 43 cycles, and the alignment of bfloat 16 requires more than 200 cycles. But when we carefully look at the wide range of the exponent distribution, we can see that the long-tail IP values actually take a small proportion. Most the IP values are concentrated in a relatively small range, and this intercept data requires relatively few execution cycles. The long-tail IP values take a small proportion, but it cannot be directly discarded because the long-tail values with large exponents have an obvious impact on the accuracy. Therefore, we can divide the floating point data into two parts. The intercept data are of heavy computation and are executed in the SIM core to achieve high accuracy with reduced execution cycles, while the remaining sparse long-tail data are calculated by the digital circuits utilizing its high flexibility. This will lead to the second challenge. The neural network mainly has two types of data, the activation and weight. Both of them need to be divided into intercept and sparse parts. So the computations will be the intercept by intercept, intercept by sparse, sparse by intercept, and sparse by sparse computation, and the final accumulation need to be calculated. The first part will be executed in the SIM core, while the other three parts and the final accumulation need to be calculated in a digital core. This would require the digital core to flexibly support various intercept and sparse processing. In addition, the third challenge, there is another optimization space for the sparsity in the floating point SIM. In previous analog SIM, we can reduce the power consumption by lower current charge and lower ADC resolution, but in digital circuits, digital SIM, apart from reducing the toggle rate, we need to find a new way to further utilize the random sparsity by the left and right IP alignment shift. So corresponding to the above three challenges, we propose the designed floating point SIM processor with three innovations, including the efficient IP to int SIM core, flexible sparse digital core, and the low microwave SIM macro. Here we start from the workload breakdown of the Intensive-CIM Sparse-Digital architecture. The weight and activation data are split into the intercept and I'm not sure if you can see my screen.
Yes, we can see your screen.
Oh, okay. So
we can also see your laser pointer.
Okay. The weight and activation data are split into the intercept and sparse parts, and then after the combination, we finally need to compute three parts in the chip: the intercept weight by intercept activation, or weight by sparse activation, and sparse weight by intercept activation. The first part is of heavy computation and on the intercept SIM core for high efficiency, while the latter two parts are of light sparse computation, so they are executed on the sparse digital core with high flexibility. For the storage, all the weight and the intercept activation are on-chip stored. The sparse weight and sparse activation on-chip stored with small overhead, while the intercept weight is on-chip generated from all the weight, so it doesn't require additional storage. Based on the above workload breakdown, the proposed IP SIM architecture is presented, and the overall architecture includes a RISC-V CPU, a SIM core, a sparse digital core, and the global SRAM. The SIM core contains an IP to int transfer unit for homogeneous low microwave SIM macros and the low accumulation SRAM. In the intercept SIM core, the intercept floating point activation and weight data are fetched from the SRAM. The intercept weight data are fetched and transferred into fixed point format and stored into the SIM micro, and the intercept floating point activation data are sent to the IP-to-in transfer unit. Then the activation data are transferred into bit0 vectors and sent to the SIM micro. The function of the IP-to-in transfer unit is to convert the floating point activation vector into the fixed point bit0 vector as shown in the right figure. The transfer circuit contains two steps. The first step is the exponent alignment, and if the current exponent value is smaller than the maximum exponent, the exponent value is increased by 1, and the same bit is the current output in this clock cycle. If the current exponent equals to the maximum exponent, it enters the second step. The mantissa is left shifted by 1 bit each cycle, and the MSB of the mantissa part is the current output. This process repeats until the maximum iterations to get the bit serial vectors so as to generate the reset data. Then the transferred fixed point bit0 vectors will send to the SIM core and perform integral in-memory MAC operations. The result will accumulated using the accumulate circuits for reconfigurable 8-bit, 4-bit, or 16-bit weights. And then the integral fixed point partial sum will be converted into a self-designed 21-bit floating point data and add it with the previous partial sum in the local SRAM. The floating point normalization process is moved to the final write-back step to simplify the circuit design. We add additional 5 additional bits in the self-designed 21-bit IP format to avoid the possible intermediate precision loss. This page shows the improvement of intercept floating point SIM. Compared with the worst case of direct alignment and conventional digital floating point circuits, the energy efficiency is improved by 2.7 times and 1.5 times respectively. The evaluation is based on a 16-cycle IP alignment. The improvement can be higher if some co-design methods are considered to further reduce the bitwise of the mantissa and the exponent part. The detailed evaluation has been reviewed in our extended GSIC paper. Next, we show the second innovation, the flexible sparse-digital core. It supports both intercept and sparse MAC operations. It contains a sparse input buffer, intercept input buffer, 16 floating point MAC units, local SRAM, and sparse address generator. Each 32-bit can represent 2 floating point data in dense mode or 1 floating point data and its corresponding index in sparse mode. The activation and weight data have different index formats. The channel direction adopts the incremental index, while the row and column direction adopts the absolute index. This page shows 2 specific examples of the sparse activation and sparse weight computation. For example, in sparse activation computation, each sparse activation data will be multiplied with the dense weight matrix. The absolute row and column index reduce the decoder complexity and ensures simple address generation, while the incremental channel index reduces the index bits, so that 16 bits are enough for the sparse activation and weight data format. We also explore the necessity and efficiency of the sparse-digital core. The top figure shows accuracy on the ResNet 50 ImageNet dataset. Barely calculating the intercept and intercept part on SIM will lead to about 3% accuracy loss. Adding the other 3 parts, including the sparse intercept, intercept sparse, and sparse parts, we can recover the accuracy back to the algorithm baseline. Besides, the sparse-digital core only increases the additional energy consumption by 4.6%. The bottom figure shows the execution time of the SIM core and sparse-digital core on each layer. By parallel execution, the sparse-digital core incurs no performance degradation. Next, we show the third innovation, the low CIM macro. It contains 128 by 128 SRAM cell and corresponding adder trees. We will go detail into the low macro adder tree architecture design. This page shows the traditional adder tree that accumulates from 128 of 1-bit input to an 8-bit output. For convenience, we divided it into 2 stages. Then we observe the distribution of the MAC value of n 1-bit data. The red figure, lines with different colors represent different situations of different MAC numbers, and the top figure shows the details of the bottom figure. We can see that most accumulation results are smaller than half or a quarter of the maximum value n. Therefore, the high bit position in the result can be unnecessary. The larger n is, the more bits we can save. In the top and bottom figure, we select 2 points for both stage 1 and stage 2 adder tree, which are named as conservative and aggressive modes. Even the aggressive mode can ensure no accuracy loss in ResNet50 ImageNet. But for more compatibility for more models, we implement the conservative mode on chip. Note that this method requires no additional training efforts. Therefore, based on the above observation, we delete 1 MSB result in the first stage adder tree and 2 MSB in the second stage adder tree. Compared with the conventional adder tree, this work, the conservative and aggressive modes can save 9% and 13% power consumption respectively. Next, we will show the chip measurement results and analysis. This work is fabricated in a 28nm process with a chip area of 2.5 by 1.8 square millimeter. It can work at 10 to 400 MHz, and the minimum working voltage of the CIM macro is about 0.4 volts. This page shows the test results on different fixed point and floating point models and presents the evaluation results of on-chip training. Here we do not discuss on the detailed values, and you can reference our paper later. This page shows the comparison with the existing CIM processors at that time, utilizing the low macro adder tree and the Intensive-CIM Sparse-Digital architecture. This work supports efficient floating point CIM and shows better energy efficiency. Finally, we give some further discussion and conclusion. Since the CIM research topic is very hot, there are many new techniques proposed for floating point CIM in recent years. For example, the exponent computation can be added inside the CIM macro. The analog and digital hybrid architecture is adopted, and the CIM circuits can be reused for both floating point and integral operations, and the exponent can be grouped to reduce the power and area. Luckily, we find that the Intensive-CIM Sparse-Digital solution is still compatible to these innovations. These works focus on the CIM part design, while this work also considers outlier sparse values that cannot be well calculated in existing CIM solutions. We would also like to share one observation or one view, which might not be totally accurate. Most existing CIM solutions are actually using the integral CIM to realize the floating point CIM, either in analog or digital way. That means even if the CIM circuits themselves are accurate, the results may not be identical to the standard format, such as the IEEE 74054 IP standard baseline. Since the computation order is changed and the bit truncation, the bit positions of the normalization would make the result different. So we may require further research on the floating point CIM formats or standards to evaluate the accuracy mismatch compared to existing solutions such as on the GPU. We would also like to show the research roadmap of our group and illustrate why we explore the floating point SIM. Firstly, we start from the SIM circuit exam itself to show that this way is possible together with the sparsity and SIM combined to achieve high metrics. Then we add the floating point function and the heterogeneous cores to enable more functionality for complete AI algorithms. And then we try to optimize the system level SIM metrics to achieve higher system level metrics and the whole system make it better. But all these things do not touch the off-chip DRAM part. All these things make the on-chip energy efficiency better, but we do not consider the off-chip DRAM. So that's our current research focus by integrating multiple SIM devices and chiplets to achieve high scalability for larger models. So back to conclude this presentation, we design an energy efficient SIM processor that supports floating point computation using the Intensive-CIM Sparse-Digital architecture and achieve high energy efficiency. That's all. Many thanks for your kind attention. Yeah.
All right, thank you very much. Jinshan, let me pause the recording.